Let's write again our expression for the wave function. And let's group terms related to the wave vector little k. Our original expression is then nothing but a linear combination of the eigenfunction psi and k, where n is the bound index. Note the coefficient a and k, which is still unknown. This is because we have not specified any boundary conditions in our problem. Each eigenfunction psi and k is expressed as the product of a plane wave k times an envelope function which is expanded using the reciprocal lattice vectors bk. As a result, the envelope function has the periodicity of the crystal, which is also true for the modulus of psi. This is known as Bloch theorem, and psi k are called Bloch waves. This was discovered earlier by Floquet in 1883, but not in the context of quantum mechanics. Note that although this proof of Bloch theorem has been done using a plane wave approach, Bloch theorem is still valid and holds for any approach as long as the crystal is perfectly periodic. In practice, infinitely periodic crystals don't exist, since they must have a finite size and might not strictly be periodic due to possible defects or impurities. Our idealized model is still very relevant, as lots of real-life crystals closely approach this situation. At this point, our method can give us information about the valence electrons, such as spin distribution, as well as electronic density of states. This can now be used to determine some macroscopic properties of the crystal, such as the electrical conductivity or the optical absorption emission profile. So, how does the plane wave approach perform in real life? Generally, the plane wave method works well for potentials that are weak compared to the free electron kinetic energy. This is notably the case for the conduction bonds of aluminum. This is also the case in electron diffraction experiments in which kinetic energies are orders of magnitudes the potential energies. A slightly modified version of the plane wave method is in fact an industry standard in electron crystallography. One of the biggest weaknesses of this approach, though, is its ability to accurately represent the wave function of arbitrary shape. In practice, the wave should look like a combination of a rapidly varying part around the nuclei and a more smoothly varying part in the interstitial part. As a result, a very large number of plane waves might be required, which may compare unfavorably to other methods such as KKR or APW.
As much as I would like to carry on these fascinating topics, this episode is now drawing to an end. I hope you found it plain and simple, or crystal clear. If you did, don't hesitate to wave me a like, and I hope to welcome you soon again on Crystal Panic 2.